assistant professor at Stanford University. He's thought about a lot of things sort of in the space of robustness, distribution shift, reliability, fairness. He kind of has this very unusual but very good knack for doing both very interesting kind of theoretical research as well as thinking of really clever sort of experiments and benchmarking, also running really kind of large-scale studies. And I'm sure he has something great in stock for us today. And Tatsu, please take it away.
Thank you very much. This will be a little bit of a sharp transition from the last couple of talks that we've had. This is very non-theoretical in some sense. But I want to talk a little bit about sort of distribution shifts and gaps between train and test and how sort of taking a data-centric approach might help us. So really to set the stage, I really just want to start off by talking about language model generalization and just in general how remarkable this is. Looking back at say T5, Google's multitask model. That was kind of the first time in which there was this single large-scale model where you would feed in sort of multiple tasks, and this large pre-trained model would competently perform kind of all of them. And we look at the kinds of things that people are asking ChatGPT and other language models today. We see an enormous diversity of different kinds of tasks. This bottom figure over here, this one comes from LMSys1M. This is a paper where LMSys, which is at Berkeley here, they have a public API. People sort of interact with these chatbots, and then they sort of classify the kinds of things they ask. And you've got software queries, you've got like cultural inquiries, like summarization, and some not safe for work stuff that I can't explicitly even mention, right? And that's a big diversity of things that people are asking chatbots to do. And that's a really large space of things to generalize to, and that's pretty great and amazing. At the same time, there are a lot of things that these models also don't do well at, right? Like we've been hearing about these throughout the workshop. But I'm going to talk a little bit about things like niche entities. Language models are really, really good at answering questions about entities that appear thousands and thousands of times on the internet, right? Like these kinds of facts are very pervasive. It appears during pre-training. And in fact, asking a language model sort of directly is even better than using retrieval. So taking a document that's relevant and putting it in its context, which is a little surprising. Now the way in which language models are being sort of stress tested is on things like really challenging cutting edge knowledge. GPQA is kind of one of the hardest benchmarks by some folks affiliated with Anthropic and NYU. And they've been trying to ask questions that don't appear directly on Google, right? In a sense, sort of really trying to go for niche but really advanced knowledge. And finally, sort of calling back to some of the earlier talks by, say, DE, there's different cultures and languages for which these language models just don't do well because there's just not enough data or internet data available in those kinds of cultures or countries. And so I want to kind of talk about this gap, right? We see that in the sort of tails of the distribution, language models still struggle, right? Even though we as a field have come quite a long way. So I want to talk about two particular ways in which there's distribution shifts and how to close it. So the first theme I want to talk about is sort of pre-training data distributions, right? If you have a sort of naive mental model of how pre-training works, I think this is kind of what your mental model of what pre-training might look like, right? So on the left is pre-training data, random websites that are high quality, in quotes. And so things like Stack Exchange, right? And so there's this nice narrative description of how to write an algorithm. And at test time, of course, you're not going to have the same format, right? I'm not regurgitating a Stack Exchange website, but I'm doing some programming task at test time, and that's very similar, right? So I taught a language model in class recently, and one of the exercises was go download a raw common crawl dump and look at some random websites. And I think one of the things that's very telling is if you look at random websites from the common crawl, the majority of them, like a really large fraction of them, are just not good websites. They're like this. This is I picked the very first website in a common crawl dump. It's blog spam about some like software tutoring thing. It's really truly not informative in any meaningful sense, right? And so pre-training, we think about as taking high quality websites and generalizing to tasks and so on. But it's not really magic, right? Like the generalization we see is built on careful hand engineered data selectors. And this is, I think, a kind of a black box because we don't know what data is in there. And also, like, it's really hand engineered. What effects are these systems really having? And so we would like to move towards like a more algorithmic approach to thinking about data curation and selection. The second thing I want to talk about is kind of this problem of tail knowledge. We know that language models struggle, and we've talked a bit about things like hallucinations. And that's going to happen out in the tails where these sort of entities and sort of relations are not really popular on the internet, right? So LLM performance depends strongly on the frequency by which facts appear. And so data efficiency, I think, is an increasingly important theme. People are saying things like, oh, well, we've gotten the many easy gains from public data. And so what remains is sort of getting tail knowledge, advanced things that language models should learn from, say, textbooks or proprietary data stores. People are increasingly making arguments that the current scaling paradigm isn't going to hold up because maybe we can increase compute, but the amount of available text data isn't going to increase, right? That's a very slowly growing pool. And so fundamentally, I think we need maybe more data-efficient ways of doing pre-training-like things to capture tail knowledge and to think a little bit about this sort of looming data barrier in the background. So the broad approach that I'm going to take in this talk, I'm going to describe two works in this talk. The broad approach I'm going to take is that I'm not going to try to reinvent pre-training. We know autoregressive language modeling losses and so on. That works, right? There's a recipe that works. So I'm going to try to work with that recipe. And in particular, I'm not going to change the algorithm or the architecture. I'm just going to think about selecting or synthesizing data, right? So sort of the outer parts of this pipeline. So I'm going to try to use the modern pre-training paradigm, but I'm going to address some of these domain and task mismatch issues that I'm describing here. If people have questions, also feel free to shout them out or ask them as I go. I think I've sort of paced this, so we should have time for that sort of thing. So the first part, was there a question? No, OK. The first part is in selecting data for pre-training. So what I would like to do is to close this gap. Pre-training is about next word prediction on this large collection of internet documents. And what we would like to do is to solve benchmarks, to have systems with some knowledge. I would like to close the distribution gap between the two. And this is very recent work with Tristan and Chris. So I'm going to focus on data here as a way to close the gap between pre-training and sort of deployment or evaluation. And the reason why I'm going to pick that is because if you look at a lot of the people building these systems today and their sort of empirical experiences, data always consistently shows up as the thing that has had a huge difference on the performance and quality of these models. I've just cherry-picked one example, but if you look at the Llama 3 technical report, they say at the very beginning, we think 3 things are really important for building good language models. This is our secret sauce in some sense. It's the data, it's the scale at which they train the models, and I didn't show the third one, but it's sort of simplicity, right? They're managing the complexity of their entire training pipeline. And so clearly data is really, really important, but at the same time, what works is very frustratingly opaque. It is also frustratingly ad hoc. So if we look at the Llama 3.1 paper, this is a little bit of a caricature, but they don't really tell us very much. They're like, we use a variety of data sources, and we apply several deduplication methods. And some of these are described in detail, but very basic stuff like, well, do you use books? How do you mix the different data sources? Those are all not really well described in any of these technical reports. And part of the reason is because it's not any clean, nice algorithm at play here. I'm going to repeatedly refer to this paper on DataComp LM. This is a recent effort by a large number of people, some folks at Apple and so on, who attempted to do basically a bunch of data ablations. They said, let's replicate a really high performance pre-training data selection pipeline, right? And you look at what actually sort of worked in the end. It's really this large collection of human hand-engineered objects. There's an English filter, there's a page length filter, a repetition filter, a duplication filter with a Bloom filter. There's a fast text classifier that classifies bigrams. Put all of them in there, and at the end, you filter out 1.4% of the original pool, and that gives you a very high-performance language model, right? So it's very, in some sense, handcrafted, hand-engineered object. And if we look even deeper, it's even more sort of infuriating because the state-of-the-art or the best-known performing data selection system is this bigram classifier. And you're like, OK, what is it classifying? It's classifying random websites from high-scoring posts from the Reddit Eli 5 subreddit and a open source instruction tuning data set called Open Hermes, right? It's like, what? Why Eli 5, right? I'm not explaining anything to a 5-year-old. This is a kind of bizarre thing to try to filter your data on.
Sorry, what are the labels here?
Right, so you train a classifier to distinguish your positive class is these two things, like the Reddit pages and this Open Hermes thing. And your negative class.
The positive ones are like 5.
Yeah, right.
The negative ones?
And the negative ones are random pages on the pool, right? So these are supposed to classify those to find things that are like these two, right? And this works, right? From an engineering perspective, they have built a thing that performs really well, right? Like the ablations and so on show that's very clear. But to me, this is deeply unsatisfying because it requires all of this human engineering that's difficult to understand. And also, it's not really something where we can control the amount of distribution shift. We can't target a particular benchmark or do anything else. So I would like to build a simpler, principled, algorithmic alternative to this data filtering, data selection pipeline. And just to be clear about the type signature of what we're going to do, the inputs are going to be some target benchmark that I would like to do well on, the token count that I'm going to pre-train on, and the pre-training corpus, the big pool from which I am allowed to select. And the output of some data selection algorithm, in the end, should be a data filtering policy, right? So you select pages that hopefully help you with your target benchmarks. And of course, we're not the first to think about this. There's a really rich, large literature on how to think about data selection. I've only taken a small subset of this, but I'm going to mention the ones that are probably most relevant to what I'm going to do. There's a class of methods that basically attempt to build regression surrogates, basically build a model that takes you from basically a collection of data, like an indicator saying, if I include these pages, what will my performance be? You basically build this big surrogate regression model, and you optimize against that surrogate. So that's a class of things that's like data models. There's a basically Taylor approximation style thing. So you build or you look at the model's losses, and then you build a first order Taylor approximation, and you ask, if I perturb the weight of any one of the points, how does the stationary points move? How does that affect the loss on my benchmark, right? So there's approximation-based methods. And then there's many others involving like filtering things that are similar to or not from the benchmark, or using some form of like robust optimization to select pages. I think the unfortunate thing, though, is that none of these algorithms have really moved the needle. There's two sort of papers that have very recently attempted to do large-scale third-party empirical evaluations of these kinds of data selection algorithms. And basically, both of them found that sophisticated data selectors don't work. The only marginally positive result was found in the NVIDIA one, where they said that n-gram style algorithmic filtering, where you select pages similar to your benchmark, leads to very slight improvements. And we've already talked about data comp LM. The best thing they found was this very handcrafted pipeline. OK, so pausing for a bit. Oh, sorry, yes.
These vector methods are assuming we actually have given a pre-trained model, and then we basically use those policies to do post-training.
No, this is for pre-training. So we don't assume that there is a pre-trained model. You just have this big pool of pre-training data, so the websites, and you're trying to select which websites to pre-train on, or which books or whatever other sources of text. That's right. Is in some downstream benchmark, and that there's a collection of standardized downstream benchmarks people usually evaluate on, but you can sort of abstract that out as saying like there's a couple of QA question answering or common sense benchmarks that you've decided are your targets. Okay, and so sort of stepping back here, why is this algorithmic data selection so hard, right? Like why has empirical progress been so elusive? If I were to pick just one reason, I would say it's the cost. Right? If you think about it, getting any amount of data, so an algorithm that selects data points, that has to know which data points are good or bad. Right? You need to get evidence about the value of data. And in some sense, that requires you to train models, right? Because otherwise, you don't really have any other way of reasoning about the behavior of the system. So it's very, very, very expensive to get data for this task. You're training these big pre-trained models. Maybe you scale them down a little bit, but still, that's very expensive. The other issue is, you're training these small models. Those have very suboptimal data mixtures. And then you're going to extrapolate out to hopefully an optimal policy. Well, you need strong, robust validity of any surrogates that you build. Finally, because of the expense, you can only maybe get like 10 data points on how good a data selection policy is. You've got to have a really data efficient learning algorithm. So yes.
Take a step back, it seems the data selection process has a lot of design choices, like in terms of how you select what type of quality of web page to include, what's a good kind of relevancy classifier, tokenize like a lot of design choices. Why do we think that there exists a policy that can get this very rich human prior driven process?
Yeah, well, I guess there doesn't necessarily have to be a human prior. Like written down as an optimization problem, you have a benchmark. You have a black box that ingests, training data and emits a benchmark score. You can think about this as a pure optimization problem, right? Like in that very abstract sense, you might hope that you can optimize this input-output process. I think the reality is that optimization of this kind is just so complex that we need to do a lot of handcrafting. But in principle, right, you can think of this as an optimization problem. Yes.
So I guess regarding that, I mean, if you have different data mixtures, like the kind of maximum, like the lowest entropy, like the lowest loss that you could get could differ, right? I mean, if the optimal mixture has like a much higher entropy,
yes,
and like just because you're getting a higher score doesn't actually mean you're doing worse, right? I mean,
right. This is why all the evaluations and sort of when we think about how good a data selector is, we evaluate on a benchmark, not on log losses of the next token, because as you say, that thing moves as you change the data mixture. Yes.
Yeah, so I'm also trying to understand like how we will like how do we think of like doing better on the benchmarks, downstream benchmark? Like, is it like if I didn't do any data selection and I just trained on the entire corpus that was available to me, compared to that, if I had selected somehow?
Right.
Exactly a notion of checking how well.
Yes. And I think the reason why these papers are a little bit harsh on the algorithmic selectors is they found that no selection or like uniform type selectors actually do roughly as well as the algorithmic selectors. And we also find similar results. Yes.
What granularity are you doing this? Like, is that the granularity of like entire data sets or like websites?
That's very good. Yeah. So it depends on the algorithm. Usually they have like 10 to 20 coarse grain domains that they filter over. Or they, n-gram-based methods will just operate over individual pages. Yes.
I think you were talking about data, but it seems to me this data selection problem, if we have a, say, target benchmark is a subset of, say, augmentation, because in augmentation you can use like a density ratio match, assign a weight to different instances, where in this case I just assign binary mask to each of the original one. If I have a target benchmark in mind.
Yeah, so this DSIR method is exactly like a density ratio idea. They look at n-gram statistics and say, let's try to match the density ratio, like try to shift the distribution to have the right statistics. So there's algorithms inspired by exactly these ideas. Yes?
So when we think of like the cost, like expensive to get data, how should we think of this in these cases? Like if there's already some pre-trained data, like so what is, on top of it, are we going to get some labels or are we going to get some kind of like, oh, this is better or worse kind of?
Yeah, just to be really concrete about, let's say, how like OpenAI or Llama might do, or sorry, Meta might do this. The standard procedure for something like this right now would be let's say you're building a 7 billion parameter model. You would scale it down, let's say, to like 1 billion. And then you would train a bunch of 1 billion parameter models on handcrafted different sort of, data mixes you think might be good. And then you would look at the small scale thing and then you scale it back up. So each data point is usually like a smaller scale training run that's supposed to be a surrogate for a larger training run.
The thing to look at is the scaling. Is that
that's right. Yeah, that's right. Yeah. So the more sophisticated data selectors all look at the scaling behaviors, and then you try to scale down as much as possible to reduce this. The naive stuff would imply training a model at scale, which is non-starter. Okay. So, oh, sorry. Yes.
Last little might be orthogonal, but are you not concerned at all about overfitting the benchmarks? I could believe if you throw out together, then you might lose something.
Yeah. In the abstract, that is very much a problem. In reality, our ability to optimize benchmarks is so bad. This is a complex black box input-output problem that empirically we are not very concerned. Like if we can get to that point, actually we've like achieved a lot because we understand quite a bit about how data affects outputs, right? Okay, so let me walk through a very concrete example. This was already answered, so I'll do this a little bit quickly. I want to train a new like Llama 4 or something, right? A 7 billion parameter language model. So how would we do this if we followed one of the standard approaches like data models? I'm going to train 1,000 models. Maybe I'll train models that are slightly smaller than 7 billion. But if I care about some of these like advanced capabilities, maybe I need to stay pretty close, right? And each of them needs to have a different data mix. I don't know what data mix is optimal, so maybe I'll just sort of randomly perturb my data mixes. I'll measure my benchmark performance for each model, and then I'm going to form a regression from the data mix to the benchmark performance, right? Like, this is a very naive, very straightforward thing. This is a non-starter because I'm training 1,000 models near the scale that I'm going to be doing training, right? This is incredibly expensive, just not really going to work in any sort of meaningful way. OK, so the core idea, like the first trick of this part of the talk, is we're not going to train any models. And the reason why we're not going to train any models is because people have trained a lot of models for us already, right? You go on the internet, there is an extremely large collection of language models that are already pre-trained and that someone has uploaded, right? So now there's no cost. These cover a very large heterogeneous space of models, right? Different tokenizers, different architectures, different data mixes. Some of them are code models, some of them are not. And there's a pretty big sample size. There's about 100 models that are credibly high performance on Hugging Face right now. Of course, there is a really big issue here, which is we don't know what data any of these models trained on. That's usually kind of like a trade secret kind of thing for a lot of the companies releasing these models. But we can kind of see that there's a lot of potential here, right? People have collectively spent hundreds of millions of dollars of VC money training these models for us. Why don't we want to use all the available information that we have? And really, the core problem is we don't know the data mix, right? We don't know that model X trained on these sets of websites. It turns out that that is not a problem. There's sort of a fun way to sidestep this issue. And what we're going to do is we're just going to make a strong, but maybe OK hypothesis or assumption. I'm going to hypothesize that there's a single index model that relates the log losses. So this is a vector X, where each entry of that vector is the log loss that I suffer on a particular web page. And there's a single index model that relates this to downstream performance, right? So there's a linear term, and then there's a nonlinear term F that relates these two. And then in step 2, if such a single index model exists, and let's say that there is a set of weights here that are also non-negative, like these theta stars that are good are also happen to be non-negative. Then notice that this inner product, I can just rewrite this as an expectation, right? Any non-negative set of weights can be normalized into a distribution, and I can shove that constant into F. Now, so that means optimizing this weighted loss, where I sample according to theta star, is basically equivalent to optimizing the single index model, which we hypothesize is monotone with the benchmark performance, right? So the one-liner describing this is saying, if we can find a non-negative single index model that relates loss to performance, sampling according to those weights is a good data selection policy. Yes?
When you say log loss, what do you mean is the log probability that the commercial model assigns to this?
Open weights model assigns to this particular website, right?
Yeah.
OK. And so this leads to a very simple algorithm. I will explain what exactly this gamma j is and where I get it first. But we're basically going to use a high-dimensional regression estimate, where I'm going to take this correlation quantity. I'm going to look at pairs of models, yk and yl. Whenever yk's benchmark performance is better than yl, I'm going to look at the difference of their ranks in terms of their log probabilities. I'm going to show that this is a consistent estimate of the single index model weights. And then in the second step, what I'm going to do is I'm going to take tokens, take domains, sort them by largest to smallest gamma, and then I'm just going to take tokens in that order of those domains until I exhaust my token budget, right? So this is a very simple algorithm. I'm essentially computing a kind of generalized correlation coefficient, and then I sort domains by that correlation, taking tokens from most to least correlated until I run out. So just to explain, why is this a reasonable thing to do at all? That gamma thing that I put up kind of seems very non-standard. But actually, this is just a very simple extension of some classic results in sort of high-dimensional geometric estimation or high-dimensional estimation of single index models. So from a pretty classic paper, Plan, Virchin, and Udovina in 2016, they show that if you have a single index model where the covariates are distributed as a Gaussian, you can basically show, they have finite sample results. I only have the expectations here, but you can show that the expectation of y dot x is some constant times theta star of the single index model. Chen and Banerjee had this slightly more robust version where now the y's only enter in through the signs, where they show that the inner product of these signs and the difference of the x's is once again equal to beta, a constant, plus theta star. We found that both of these estimators use the x values directly, and that tends to be pretty unstable. X values can vary widely because some model might assign very low probability to a particular web page. And so we robustify this, and we're going to put ranks on the x's. A result, honestly, that surprised me. We came upon this originally very empirically. My student, Tristan, was looking at this estimator, and he said, actually, if we just turn these into their ranks, the whole thing starts working. And then so we tried to work backwards and say, like, is this actually a consistent estimator? And that turns out to be true. If you compute the expectations involved here, and you look at essentially the Chen and Banerjee estimator, but with quantiles instead of the raw x's, you can show that actually the same kind of result. You get the consistent estimate of the theta star, sort of non-linearly but monotone, transformed through an arcsine function. And so if you recall, this estimate is exactly what we compute as our correlation coefficient. Now, what we want to do is we want a non-negative theta star. Getting constraints on our sort of high-dimensional linear regression is a well-studied problem. You just do a projection. We follow some of the approaches in Chen and Banerjee, and we project this linearly under sort of the token constraints. Right? Our distribution has to sum to 1 and respect the fact that each domain only has a finite number of tokens. Yes?
How do the variances of those estimators compare?
Yeah, the variance of the estimators. So this one is much nicer behaved because of the rank structure. And the x's can somewhat be sort of like long-tailed and break some of the other estimators. We don't have a precise characterization because it's not quite clear. We only have n of 100 for some of these. But we basically found that to get the other estimators to work, we have to clip the x's. And that introduces a lot of complexity. Yes?
By rank, you mean like empirical?
The empirical CDF, that's right. And so we're cheating here if that's what you mean. We're looking at the population CDF instead of the empirical CDF. So if we were doing this right, we would have to look at the empirical and do some concentration bounds. So now I've described this algorithm. It has this kind of nice, appealing story to it. But I think the real question is, does this work? Because I opened this part of the talk by saying many things don't work. And so what we're going to do is we're going to fit this single index model that I was describing. So I'm going to take 90 public models, and I'm going to select against 8 different benchmarks spanning many different capabilities. And I'm going to train and evaluate pretty tiny models, 160 million parameters. And then I'm going to compare to any sort of selection method that's been validated at scale, so DSIR and the FastX classifier, and then pretty reasonable baselines, as well as the uniform sampling baseline. So what we find is that this thing actually works despite being really simple and having essentially no handcrafting involved. So going from the bottom to top here, lower is better because this is the average rank across the 8 benchmarks. No filtering is actually quite competitive with filtering for language, or doing the FastX classifier where we always filter for English. Removing the English filter doesn't help very much. Really, the thing that really helps is if we not only use the FastX classifier, that's the thing that works really well for DCLM, but we also match the classifier with the right language for each of the benchmarks. So some of our benchmarks are not in English, so we also do language filtering. Our approach doesn't require any of that sort of tuning and is competitive with sort of the best method that we've tested here. And if we look a little bit more deeply at the fine-grained performance, so now I've sort of broken out the performance of each method. So each block as a row is a different class of methods. Each column is a different benchmark that I'm trying to optimize for. And what you see at the diagonal over here of each block, this is basically saying I tried to optimize for ARC easy. This is the performance that I got on ARC easy. And the numbers at the top left, this is sort of the ranking amongst all competitive methods. And you kind of see immediately at a glance that our method is really optimizing for each of the benchmarks. For example, on the English benchmarks, for the multilingual benchmarks, we see that it does really badly on the English benchmarks because it's basically doing language filtering in the inner loop. The same is not true of a lot of the baselines. And also, across all the benchmarks, basically we're tied first or second place with kind of this very handcrafted pipeline that I sort of set things up at the very beginning. Yes?
So it does better for the specific task you want to optimize for, benchmark you want to optimize for. Does it also affect other data sets or benchmarks?
Right. So this is kind of the sort of, I wouldn't say trade-off, but if you're optimizing for a multilingual benchmark like German Lambda, you see that the performance on the English benchmarks are kind of worse, right? Or actually, it's the reverse. If you're optimized for English benchmarks, then the performance on the multilingual benchmarks is much worse. A thing that this does automatically is if you have an English target benchmark, it realizes, actually, I don't need any non-English capability. It immediately drops all of that from the pre-training data set. OK, the kind of observational piece, I was saying before, that we're building the single index model. And so you might ask, is the single index model predictive at all? And that turns out to be true. So each of these points is a different or publicly available language model. What we find on the x-axis, this is the actual rank that they attain on a benchmark. On the y-axis, this is the predicted rank from the single index model. We see fairly tight scatter. And so, there's, I think Sammy was mentioning this before as well, log losses, which is sort of the y-axis over here, if you wait and sort of learn them suitably, are predictive of actual benchmark performance in many cases. And then finally, sort of to put everything together, you might want to kind of understand what's going on with this algorithm, right? So the core primitive of our algorithm is this big matrix of losses across different documents and different models that we've taken from public leaderboards. And so you might ask, what kinds of structures lie within this big log loss matrix? You see pretty clearly, this is a TSNE sort of visualization of that space. You see very clearly language is very different clusters. Each of these colors is a different language. They clearly separate in this sort of space of losses by models. The other thing that's very fascinating is the other sort of very strongly encoded structure is the average complexity or the average sort of losses that models incur over the pages. So you have sort of more compressible versus less compressible pages. That's another structure that's very clearly visible in the sort of loss matrix structure. OK. And finally, I think this might not be sort of the first thing this crowd thinks of. But I think when I give this talk or talk to people, I say like OpenAI about this kind of work, the first thing they ask is like, can we trust any of these results, right? I think Max's talk sort of brings up relevant points here. Past results have not held up in this field, right? These are small-scale experiments. Our choice of pre-training data is n of 1. And I'm asking you to sort of trust me that this is externally valid for pre-training in general, right? And so to give a little bit more confidence, we're trying something a little bit different here in terms of thinking about validity of our results. We're doing some sort of pre-registration-based approaches to validating our results. And so what that means is part of our preprint was basically a pre-registration study where we said, OK, we're going to scale up by 100 times in compute. We're going to pick different data sets that we've never looked at before. And then we're going to run our algorithm with these settings without any changes. And then we're going to report both positive and negative results afterwards. And this gives us a way of really putting our theory a little bit more to the test than sort of trying different data sets until they work. I'm going to skip this just in the interest of time. And so the takeaways here is, data selection is sort of a thing that almost everybody building LMs agrees is a really important part of the pipeline, right? It's core to generalization. It's core to how well we can adapt to different benchmarks. But it's been very handcrafted. And so my approach here has been to say, can we reduce it to a standard problem for which we have tools and understanding and so on? In this case, standard high-dimensional regression. And we've seen sort of different pieces in this part of the talk, like using the single index model and sort of doing small-scale validation studies. OK, any questions on that part before I move on to yes?
One thing where you could predict the behavior of large models from small models, and use that in this pipeline and train like orders of magnitude smaller models and still get a good.
Right. So in this part of the talk, we don't do anything interventional. We never train our own models. But that is actually one thing that we are interested in, which is to combine kind of this. You can think of this like observational causal inference with an interventional approach where we train our own models to try to get better estimates. And there we would need to use some of those like small to large scale extrapolation results. Okay. Cool. Oh, yes.
Yeah. So I wonder about unintended effects of using this particular kind of selection based. So you said you don't use anything handcrafted. Of course, you're building on the handcrafted stuff that the other language models used. So one question is, could there be sources of data that you missed that turn out to be useful?
Yes.
But they assign it low probability.
Right.
And also, could there be cases where low probability actually is a good sign? Like usually it means it's junk,
right.
And it's junk because I don't know, it's like random stuff being junk
yes.
for spam bots. It's not the kind of thing you would predict from a language model.
Right.
But it could also be that low probability means that you're surprising. And this is where you have new things to learn.
Right. So just to sort of open with a clarification, it's not that we're selecting low or high losses. We're looking at correlations, right? So we're looking at domains where lower losses are correlated with better benchmark performance. But your comment is absolutely right, that we're relying upon essentially models with enough loss variability, and that this loss variability is not incidental, right? Like it's somehow like causally related to the downstream benchmark performance. And we are almost certainly missing a lot of signal without doing more like strong interventional results. And so that is needed if we want to actually like push this much further. Okay.
The question I had was, again, to think about this is like, okay, if I wanted to train a model from scratch, from this corpus, but to do well on the benchmark, right? Versus if I wanted a model to do well on this benchmark, like the similar, like I would presume similar thing I could think of instead of base selection, just because there is all these models that exist, like model selection and a mixture of those models to do well on the downstream task. Like I was wondering, like is there like a way to what of the, like in your experiment you see like the difference between the two, or like is it mainly like, oh, I do really want to train something from scratch, therefore that's not a benchmark?
Right. I mean, I think the desire to train something from scratch is much more sort of abstract basic science, at least in this talk, than to say like we really need to train it for this very obscure benchmark. You know, in the sort of bootcamp tutorial part I was talking about before, you know, lots of benchmarks are correlated. So it's not the case that, you know, all these benchmarks are behaving differently. In most cases, there's like, you know, the core, you know, knowledge direction and like multilingual direction. And so maybe you do want to use this to make a model better at multilingual stuff. But I don't quite think, you know, you need to use it to target a single obscure benchmark. Okay. So now the second part of this, I think this is a good segue, because the first part is about pre-training, right? Build the model from scratch, have it target a particular benchmark or like close that distribution gap. The second part I want to talk about is you have a pre-trained model. And you would like to teach it some, you know, small domain, like let's say a single textbook with really important facts that you would like to put into the knowledge of the language model. Like, can we do that, right? And so our approach is going to be, we're going to try to synthesize data in some way. And your mental model going in should maybe be, it's a kind of advanced form of data augmentation. This is joint work with Zitong, who's sitting here, Neil, and Shengping, and Emmanuel. Okay. So, you know, rolling back a couple of slides now, right? The motivation for this is that LLMs, especially in terms of knowledge, struggle beyond the head of the distribution. There's a lot of different results floating around, but I think this is general consensus now, that a model maybe needs to see a fact like thousands of different times in different kind of presentations before it like robustly acquires that fact and uses it in different, or is capable of using it in many downstream applications. And this, you know, really nice paper from some folks at UW show this really clearly. Like there's kind of a popularity cutoff beyond which, you know, just using the language model is good, and below which you really want to be like combining it with something like a retrieval system, right? And there are good ways of adapting a language model to a new body of knowledge, right? Continued pre-training is well studied. There's been lots of good papers on this topic. And this is really taking the same pre-training playbook and applying it to sort of new data that you didn't see, right? So in this case, you might take, let's take code llama, you know, 600 billion extra tokens of code that you found somewhere lying around, and you do the pre-training process again on your already pre-trained model. You do sort of autoregressive language modeling on these 620 billion tokens. Your model is now much better at code, right? So this is kind of the playbook that has been really successful for math models, for code models, and so on. But if you look at this, this is a little bit troubling for a lot of tail knowledge, because the smallest number here is 15 billion tokens. And that's a lot of tokens for any sort of reasonable domain of knowledge. And the successful ones like Code Llama are actually even bigger. They're like 500 billion tokens. And so we would like to really dramatically lower sort of the data requirements here. And if we can do this, then this sort of allows us to maybe think a little bit more about much more data efficient ways of updating and doing pre-training as well. And so our setting that we're going to consider, just to get your mind in the right order of magnitude, we're going to have a total of 1.3 million tokens for articles and books. And we're not going to change the algorithm. We're going to use the same kinds of continued pre-training as all of these other papers before. but we're going to do it on dramatically less sort of raw input data. Right, so this is 10,000 times less data. We need a little bit more of a something to get this to work at all. So let's step back for a moment and think about what standard continued pre-training is doing, why it fails, and why we might be able to patch it in a really sort of very straightforward, easy way. So standard continued pre-training is going to train directly on our documents, right? So let's say we have a book. All I'm going to do is I'm going to predict the next word of that book, starting from the start all the way to the end, right? So I've taken the abstract of our paper, and you have this prefix, and now the autoregressive LM is going to predict the suffix. And this is really data inefficient. And to give you one example of a problem that LMs encounter with this kind of training is something called the reversal curse, right? So if a fact appears, let's say in sort of the canonical regression order, so here, let's say synthetic continued pre-training appears before synthesizing a large corpus. If you ask, what does synthetic continued pre-training do? Maybe the model can do this pretty well because it was trained to follow up synthetic continued pre-training with synthesizing a large corpus, right? It's sort of in the right direction. If I ask, kind of the reverse, what method synthesizes a large corpus? Now, this is actually a much harder problem for the language model because it was never trained to condition on this sequence and generate this sequence, right? All things like this are, of course, very conditional to the particular experimental setup, but people have observed things like this. And this is why, if you have a single book, just training left to right on the sequence isn't really going to directly work. So let me contrast this a little bit with pre-training, right? Like we know pre-training works. Like if I ask, I don't know, Llama 3 something about Harry Potter, right? It can answer lots of different, very detailed questions about Harry Potter, even though there's only one Harry Potter book, technically speaking, right? And I think the reason for this, right, is in pre-training, we've got enormous sort of diverse sort of presentations of the same knowledge, right? There's only one Harry Potter book. That's the source of all knowledge, so to speak. But there's a lot of derivative content, right? Like Wikipedia books, Stack Exchange, QA, Reddit discussions about the book. And all of these different formats of the same underlying knowledge, allows us to overcome the underlying data inefficiency of autoregressive language modeling. And so, contrast this with continued pre-training, where we're basically just training on the Harry Potter book and hoping for some form of magic generalization to all of the kinds of ways in which we can query the model. And so we're just going to do the most naive thing here, right? I'm not going to claim that this is somehow algorithmically a very clever trick. What we're going to do is data augmentation, right? If it's the case that what we really need is pre-training like diverse presentations of the same knowledge, well, why can't we take our book, take a language model, let's say a powerful language model like GPT-4, and have it rewrite this book in many different forms, right? And if we can replicate sort of the variations in content and the variations in style and all this diversity that we have in pre-training, then we might have a hope that we can capture the same kinds of generalization behaviors that we see during pre-training, right? That's kind of the overall setup for where we are and where we're going to head in this class of techniques. And just in case you're thinking a little bit about other kinds of synthetic data techniques, this is a little bit different in how we're thinking about it from people using these kinds of methods for compute or size efficiency. There's been a couple of papers saying synthetic data gives us smaller, better models. We don't care about those. Or fine-tuning for a particular target task. We're still wanting to build a multitask system that can answer questions, that can summarize this book, and so on. We're not targeting only a single task, right? So there's distinctions from all of these kinds of ways of thinking. Yes?
How would you control for making sure that these are just different versions of the same thing and not just like a fan fiction that's just going in all different directions? So I can actually query about Harry Potter and get answer about that.
Yeah. I think this issue of like grounding and hallucination is really critical. And to be clear, we have no way of enforcing grounding. But if we contrast this with, say, methods that might try to like synthesize, websites from thin air, we're thinking about this really explicitly as an augmentation strategy. We're always conditioning on the book. And that really, in our manual inspection, does seem to ground everything out into the original book. And we're always going to evaluate on things like question answering that's going to test or that will at least, flag if we have really high rates of hallucination. Yes?
So there are two things you can do that are less ambitious than this, which I guess you decided won't work. One is, textbooks are all you need. Trained a very good model without this kind of diversity.
Yes, you mean like by sort of constraining themselves to the textbook world. Yeah, I think that's...
I mean, it was also synthetic data.
Right. I actually, like in some ways, that comment is on point because textbooks are all you need varies content, right? Like it tries to generate textbooks in many different domains and probably in many different versions of the textbook, but it doesn't vary in style. It's all textbook-like. It turns out that our approach actually doesn't vary style very much. It's mostly varying content. So in a sense, we're leveraging that core intuition still.
Okay, thanks. And then I guess the other question is, like, do you, maybe this is more about style, but the question is, do you need diversity or do you just need more epochs on the same training data?
We aggressively hyperparameter tune across a range of repeated epochs. And so all our baselines are like, very carefully tuned against that. And that doesn't help. Especially if you only use the original data, it actually does worse, no matter how much hyperparameter tuning we do than the original model. So as with kind of the last part of the talk, I try to keep myself really empirically grounded. And so to me, a really important thing is an experimental setting that has roughly the right characteristics. It has about 1 million tokens, and it has a really good QA benchmark. And there is such a data set called quality. It has a bunch of niche fiction and magazine articles, and about 1.3 million tokens. This is far too small for any of the continued pre-training methods to work. And really importantly for us, this data set comes with really high quality question answering and summarization evaluations, so we can do evaluations really quickly and nicely. Just to give you a sense of the base accuracy, if we take GPT-4 or Llama and ask it questions from this data set, it's about 50 to 40% accuracy. So it doesn't already know the facts in here, right? It knows a little bit, but not everything, right? These are publicly available things, so it has probably trained on it in the abstract. Okay, so as Jason was saying, okay, look, let's do the naive thing. Let's just tune our hyperparameters and let's do continued pre-training on just the books. So that's this green line over here, and this dashed black line, this is the original model that we started from. So we are now actually actively doing worse, mainly because we have done what people call catastrophic forgetting. The process of doing CPT has probably messed up some of the question answering or whatever capabilities in the model a little bit. Okay, so now attempt number 2 is you might say, all right, so let's go for this data augmentation strategy. And a very reasonable first cut is to say, I'm going to go through my book, and I'm going to repeatedly ask a language model to paraphrase it, right? That's a reasonable data augmentation strategy. You will get diversity. This turns out to work a little bit. We're now beating the naive baseline of doing nothing. But this plateaus out really quickly, and we don't get any gains past this point. And the reason for this is because language models, especially the ones that are available through APIs and have been sort of tuned to be products, they are not terribly diverse. If you ask for random samples of paraphrases, or in a sort of very recent related work, we were doing like idea generation stuff. In that case, if you ask for new ideas, the rate of sort of new things drops off very precipitously, right? So the diversity in the space is very small. And so an increasingly common method to get around this, and one we adopt, is to use an external source of randomness or external source of diversity. Sanjeev was talking about skill mix instruct. There, he was taking random pairs of skills and using those to basically build a diverse data set. Here, what we are going to do is we're going to have a big knowledge graph, and we're going to look at different entity relations, and sort of the space of combinatorial choices of entities is going to give us sort of an externalized source of diversity. So let me be really clear about sort of what we're going to do. We're going to take a knowledge graph, let's say, inspired way of generating diversity in content. So let's say this right-hand thing, this is a schematic of all the entities and the facts that appear in a particular document that I'm going to augment, right? So first, I'm going to extract all the entities using a language model. And then I'm going to randomly sample or enumerate k subgraphs of the knowledge graph. In this case, k is 2, so I've picked a pair of vertices from this graph. And then the augmenter LM describes synthesizes descriptions of entities in this subgraph. In this case, it might be a direct relation, right? Da Vinci and Louvre isn't connected, so our model might not immediately know it. But if we synthesize something, it might say something like the Louvre contains many works of art by Da Vinci, including the Mona Lisa, right? So now we've sort of constructed or filled out this subgraph. And so now what we're doing is, in some sense, constructing the deductive closure of this knowledge graph. We're taking the explicit subgraph that we have, we're picking random pairs of vertices, and we're filling in the rest. And these implicit facts now become explicit facts in the data, right? OK, and so how does this do? It does well. Of course, it's not magic, so it's not like it goes up immediately, but it scales very predictably and very well up until maybe around here, but even up to here, we're getting gains, right? So very predictable scaling gains because there's a combinatorial large set of vertices that we can pick, and that allows us to generate very diverse data that lets us get gains, right? And so here, this is question answering accuracy on quality. So there's multiple choice questions, and these questions are all being answered without access to the text, right? So the model is just answering them as is. One concern you might have, yes?
This is like the external knowledge graph that we already have access to, right?
No, this is synthesized from the language model, right? So the language model looks at a document and it just generates all the entities
For
a given document.
Current continuous pretraining corpus.
Yes. So you pick a random document, you get the entities, you pick random entities, and then you connect them, right? This is all synthesized kind of from scratch. There's no external additional info. Yes?
Questions. What would happen if you do some sort of regularization with respect to the pre-fine-tuned model? And then the second question is, what would happen if you do something like the parameter addition fine-tuning?
Did we do LoRa? Zitong? Yeah, we didn't do LoRa, but we do basically some form of data-driven regularization where we're feeding in pre-training data from Red Pajama v2. So we do that, and we optimize over that hyperparameter. Yes?
How do you make sure that all these data augmentations are truthful and actually to your book?
Yeah, so at least in this work, we're not doing human evals of the generated data, but we have end-to-end evals of the QA accuracy, and we have evaluations of sort of summarization faithfulness. So we'll ask the model to summarize books, and we check for factual correctness. Let me skip ahead. I'm going to skip this unless someone asks a question about whether we're just doing distillation. But I think one thing that's cool is, at the start, I was saying what we really want is a general system that understands and manipulates knowledge in this corpus. And so we took this model that we continued pre-trained, we did instruction tuning. So now it can respond to different varied instructions. And now it can do some level of summarization. It can describe books that are in the corpus. It can sort of do things like write bullet-pointed responses if I ask about the practice of dentistry, which is covered in this article. And I can sort of compare and contrast different articles. And so pairs of articles can be related, although this is all kind of n of 1. If we look closely at summarization, we can kind of see exactly that question, like how much hallucination is really happening here? Has it really acquired the facts? And so here's an example of we've asked for a summary of a particular book in the corpus called Cosmic Yo-Yo. And I've taken our method, which is up here, and then I've taken 2 different baselines. So this one is just doing continued pre-training, that's raw, and then rephrase, which is just doing random paraphrases. I've taken the liberty of highlighting things that are false in red so that you don't have to read the original book. The approach that we're taking, Entograph, makes one mistake, which is that there's no yo-yo-like device. It's a yo-yo-like, I think, maneuver that is being done in this book. Whereas the 2 sort of rephrase and raw summaries are basically entirely false. The only reason it's not completely red is because there's statements that are not actually assertions about the book. And so we do a quantitative evaluation of this, which roughly matches what you've already seen. Quality, the data set comes with human written summaries. And so the human reference is over here. And I'm measuring salient number of claims relative to humans, so the number of true things that we're saying. And this is the number of false things that we're saying relative to human. And we're doing an automatic evaluation here using GPT-4 to be sort of clear. But here we kind of see pretty big effect size differences. The method that we come up with for CPT, these are the green points. We see we have a lot of salient claims, not too many false claims, and all the baselines are way over here. They're just totally hallucinating when we ask it to summarize anything. The final result, I kind of want to, empirical result that I want to close with is to say, okay, like if you're a very practically minded person, this whole talk is kind of crazy. Because if you want a language model to acquire niche knowledge, you're not going to spend God knows how many dollars doing continued pre-training. You're going to use a retrieval system, right? And so, in sort of somewhat response to that very practical criticism, right? When we take the continued pre-training method we have and we combine it with a really, really powerful retriever, a retriever that has over 99% recall in terms of retrieving the right document, we still see gains of about 2%. And this, I think, also contextualizes our result because, originally Llama started at like 40%. And our closed book performance, so the performance without seeing the book, is about 56%. And this is actually pretty close to the llama performance of 60% over here, right? So we've actually gone really close to a full-on retriever system without ever having retrieved documents. Okay, the last thing I want to end with is just kind of thinking a little bit more mathematically and theoretically about what's going on, right? There's no free lunch here. The amount of information contained is still in the book. I kind of wanted to understand the scaling behavior and what we can possibly hope to get out of this. So why do we get gains from diverse rewritings of the original data? So I'm going to build a toy mathematical model based on this knowledge graph intuition. And the setting is that I have a single document D source, and I have a set of entities V, and claims that appear are going to be represented as sort of edges contained within this document D source. As a generative model, I'm going to assume that the direct facts that appear in this document is just the Erdős-Renyi graph with independent probability P of an edge and sort of the rate here of lambda. And that's sort of just normalized by the size of the graph. The way in which we sort of mathematically model the augmentation process is filling in the gap. So we randomly select a pair of entities, just like we do in the actual algorithm. And we have to have a way of saying, like, OK, training on that data, what does that do to our model, right? So we're going to have a very simple memorization model. So whenever we have a relation between x and y, I'm going to do a breadth-first search to try to connect these two entities. And then I'm going to fill in sort of every relation from x to the first element of the path, x to the second, and so on. And then finally, a direct connection of x to the target. And so all those facts are just going to be memorized by the model. And sort of our success criterion is how much can we fill up this matrix, right? How much can we make all the implicit facts explicit? And this is really just a question about how much do you fill in sort of the giant connected component of an Erdős-Renyi graph. We have a result kind of showing kind of the upper and lower bounds of how much of sort of the edge density we fill in. And we can sort of think about this asymptotically. I think this is the clearest way of thinking about it. Let's say we take the limit as the number of steps t goes to infinity. Sort of these terms just become 1. And you get sort of a upper and lower bound that's p plus c lambda. And this quantity is p, which is the edge density, and 1 minus rho, which is sort of the size of the giant connected component in the Erdős-Renyi graph. And so this should roughly match your intuition. If we're just connecting or making explicit these like paths that already exist, then the size of what we know is the connected component in the original knowledge graph. We also have a characterization of kind of the functional form, let's say, of this process. And we sort of show that it's a mix of exponentials under a particular approximation of the growth of the Erdős-Renyi graph. A nice thing here is that if it's a mix of exponentials, we should be able to fit the observed accuracy trends of our method well. And that turns out to be the case. The goodness of fit here is reasonably good in terms of predicting what our sort of QA accuracy looks like as a function of the number of tokens. Of course, this isn't really as stringent of a test as we'd like to have, but it at least validates some of the really basic parts of this. So OK, I think I'm at time. We're very close to time. And so I'll wrap up. This part is trying to show that language model pre-training style learning can be adapted even to data poor domains by just thinking about kind of data augmentation style intuition, right? We ask a big language model to generate sort of like diverse augmentations of the data, and that allows us to learn from this domain. We have now effective continued pre-training not at the 50 billion token level, but all the way down to the 1 billion token level. And it can even approach the performance levels of retrieval, which I think is really exciting. And in the future, it's going to be increasingly important to think about like data efficient language modeling. Compute will keep growing. There's a lot of investment in that. Data doesn't grow quite as quickly. OK, so putting all this together, the thing I wanted to really emphasize is this idea that we can do a lot just thinking about the data. And we can even think about the data algorithmically, right? It doesn't have to be this horrible, messy empirical piece. And data has a lot of leverage because we can use sort of a lot of the effective algorithmic components that people have been building up over the last many decades of language modeling. I'll keep it short, so thank you. Jason?
Actually, there's one over here.
Sorry. Yeah.
So the question is, when you build up this graph and you do this synthesis, is it possible that like this is different from rephrasing with language model by just grounding language model on this graph. And then
Or I guess I wouldn't say grounding. Like even rephrasing is grounded in the sense that it gets a passage. The difference is that we're adding sort of external controls, right? In the rephrasing case, we're just asking the language model, please rephrase my text, right? And that's a very limited set that we can get out.
but in the other case, you sort of scaffold with this structure.
Right. In some sense, like I think a thing that we've seen in all these like synthetic data style results is that you externalize the diversity. Like you don't just sample from the model in the hopes that a generative model is diverse. You do conditional generation where the thing you're conditioning on forces the model to output many different things.
So I think one baseline that I can think about is you can just ask a powerful language model to create QAs on these books and then train on them.
Yes. And one thing I didn't mention is the rephrase baseline also includes QA because the previous paper, like Rephrase the Web, actually had QA as one of its rephrases. It doesn't have any externalized diversity, which is why it doesn't succeed. But we do have that as part of the blue line. Yes.
So this might be related to the question. Do you think that there might be something which is vastly better at extracting information, or sorry, extracting parameter updates, I should say, from reading the newspaper? Like I feel like when I read a newspaper, better yet, when I read an archive paper, I'm actually learning something permanent by doing, like maybe it's like generating questions and answers or other additional text that's synthesized, and I'm just remembering my chains of thought. But it feels much more data efficient.
Yeah.
If you learn something by taking a class, like there's not that many tokens when you go to those lectures and do those homeworks.
Yeah. I mean, in a sense, I feel like this is the brute force thing that works is one way I'll describe it, right? Like, I think the real hope would be you have this data efficient algorithm that you just show it the book once, and the loss function and architecture is so good that it does the continued pre-training one shot. I think that's a little bit too extreme, and I think what you're describing is something on the spectrum here, right? Something that's more data efficient that doesn't just brute force kind of the data augmentation problem. I'm not quite sure what that looks like. Non-autoregressive models is maybe one class of things that I would hope is more efficient, for things like the reversal curse. But I'm not quite sure. I don't think I've seen something that's credible as a solution to that.
I'm kind of wondering what human learners do. And it's possible that human learners are not actually, orders of magnitude more efficient than this. So, it's just that's speculation.
Yeah.
But if they are, it might be producing many new representations of the data, which are sort of indexed for later retrieval.
Yeah, I think.
Which is not unrelated to what you're doing.
I think things like BabyLM are a good example of thinking about, like cognitively plausible learning rules. I'm not sure how that really relates, or if the final solution of how we construct these things should be inspired by sort of human learning rules. I think that's all sort of open questions to me.
Oh. One more question.
Yeah. So since a knowledge graph is created for the document, how does it compare to using that knowledge graph to answer the QA?
Oh, I see. Like storing the knowledge graph?
So right now, if if I'm going to, I guess there are maybe two sub-questions here. One is how much does it take to create the knowledge graph?
Mm-hmm.
How does training on this knowledge graph and then doing QA compared to just using the knowledge graph?
Right. Yeah, in a way that's very similar to our retrieval baseline, right? Like the retrieval baseline is retrieve the document at test time, don't build a knowledge representation, but go straight. That does work pretty well, right? We see numbers close to, or actually numbers that exceed the closed book performance. But I think I would maybe argue that's not quite partially the point, because the goal here is to say, I want to put everything into the parameters. I'm motivated originally by the basic science question of how good can we get a model just by itself, the parameters, without any sort of scaffolding at retrieval time, or test time. And that's sort of why I'm studying sort of continued pre-training here versus retrieval or knowledge graph related structures at first time.
So in a way, this is looking at if you give all this knowledge and train on it, you want to how much of it has memorized enough to
use it at test time, right? Yeah, because I think a big part of it is as compute costs go down, scaling this kind of thing up further becomes more and more viable, whereas retrieval doesn't quite have the same kinds of properties. And so I'm hopeful that sort of as compute becomes more plentiful, this kind of thing actually becomes better and better.
Maybe we can take it offline, because I was wondering, because if we continue to expect over time new things being added, we always want a new thing to be summarized.
That's right.
Answers to be answered.
Yeah.
Right? So I guess I was curious about.
Yeah, those are actually quite challenging. And even worse, I think, would be things that are temporally localized, like the current president, right? Like you want to throw that knowledge out and put a new one in. This does not have solutions for that.
All right, let's thank Tatsu again.
We're back at 1 for nonstop.